everyone. In this video, we're going to take two linear passive networks, two-port networks, and we're going to connect them in series. And then we're going to see how the Z parameters are going to change. So let's begin. Suppose I have two networks. I'll call one of the networks as R and the other network as S. And they're connected in this manner. So this is the linear passive network named R. This is the linear passive network named S. Now let's consider that this is the kind of series connection that we've given the two networks here, such that this is going to be current IR1 and this is going to be IR2. And similarly, this is going to be IS1 and this is IS2. Now, it'll be interesting to note that we are going to consider this particular voltage as VR1 and this voltage as VR2. Similarly, we'll have this is VS1 and VS2. So, having said that, the voltage over here is going to be VB, and here I'm going to call it as VA. And the overall voltage over here in this manner is going to be V1, and here it is going to be V2. So to say that this is still going to be port 1 and this is still going to be port 2, just like how it's port 1 for this network and this network both, just that they're connected in series. Now let's see how the impedance matrix is going to get affected. So let's write out the equation in terms of the Z parameters for this two-port network. It's Z11I1 plus Z12I2. V2 is Z21I1 plus Z22I2. Now this is going to be applicable for both network R as well as network S. So having said that, I'm just going to use the subscript R for the parameters related to network R and subscript S for the parameters related to network S. So when I do that, I'm going to get these set of four equations. So the ones written in the blue is for the linear passive network R, and the one written in purple is for the linear passive network S. Now let's look at the overall configuration of the two networks connected in series. In this case, what is V1 at port 1? So V1 overall is going to be equal to VR1 plus VS1. So VR1 plus VS1, and V2 is going to be VR2 plus VS2. You might now be wondering what happened to VA and VB. Now, to ensure that this particular two-port network functions correctly without any circulating currents present in it, we have to ensure that VA and VB are kept at zero. So that would ensure that there are no circulating currents available over here. Because that in case is available, then the entire equation for each of these networks would change. So assuming that VA is VB is 0, we can consider this. So having said this, now we can replace the expressions for VR1 and VS1, VR2 and VS2 over here from the four equations that we've already written. So when we do that, we will get V1 as Z11R plus Z11S I1 plus Z12R plus Z12S I2. Why do I say so? That is because whatever is entering this particular network should also come out. And in this case, IR1 plus IS1 is going to be the total current entering the port 1, and IR2 plus IS2 is the total current entering the port 2. And therefore, I1 and I2 is also going to be the currents leaving the ports 1 and 2 respectively. So now we can write this equation in this manner. Similarly, we can say this is equal to Z21R plus Z21S I1 plus Z22R plus Z22S I2. So from this equation, we can say the overall Z11 is going to be Z11R plus Z11S. The overall Z12 is the sum of the Z12s of the two networks, and Z21 is going to be Z21R plus Z21S. Z22 is going to be Z22R plus Z22S. This means we are just going to add ZR matrix with the ZS matrix so that we arrive at the overall Z matrix in case the two networks R and S are connected in series as shown in this configuration. So therefore, for a series connection of the two port networks, we have to remember that ZR plus ZS is equal to Z. Let's apply this concept to a numerical problem. So this is the problem that we've been given. This is a section which has to be connected to an identical section just like this in series with each other. So effectively it should appear in this manner. So we have this 2 ohm, this 2 ohm and this 1 ohm connected with this section in series. So this is 2, 2, 1, 1, 2, 2. And we have to compute the impedance matrix for this network. So if we are able to compute the impedance matrix for this network, it will be easy for us to compute the impedance matrix for the overall network. Because after all, if you are calling this as network R, network S is also going to be identical. So Z, the overall Z is going to be ZR plus ZS. Here, this is actually a T equivalent of a reciprocal network. So Z11 is ZA plus ZC, which is 3 ohms. Z22 is also 3 ohms, and Z12, which is Z21, is ZC, which is 1 ohm. So therefore our ZR is going to be 3113. So is our ZS. Now, since the two networks are in series connection with each other, therefore the overall impedance can be found out as ZR plus ZS. Therefore, it is going to be 3113 plus 3113, which turns out to be 6226. Therefore, the overall Z11 for this particular network, the modified network, is 6 ohms. Z12 is Z21 is 2 ohms, and Z22 is also 6 ohms. So in this manner, we can compute the overall impedance of a network which is formed by the series connection of two port networks. So that's all with today's video. I hope the concept of interconnection of two port networks in series, and computation of the overall impedance matrix for the final configuration is clear to you all. If there are any queries, please do not hesitate to post them in the comments. Thanks a lot for watching.